Thank you everybody for having us here at Team Dominator. You can see Curtis and Sean and Mark here. We're all part of the Team Dominator science mission. We launched a rocket into a tornado, an EF4 tornado, 3 years ago now. It seems just like yesterday with the pandemic, but just before the pandemic happened was when we launched that rocket into an EF4 tornado. Curtis custom built the rockets to house our miniaturized sensor. Mark has built the miniaturized sensor and all the technology that live streams the data from inside of the tornado down to a ground receiver. He'll talk about that. Curtis will talk about the rockets and the launcher with the pan and tilt capability. Sean's going to talk about what it's like to drive the Dominator 3 and be the pilot when I'm yelling at him from the top of my lungs. Everybody's going crazy. Rockets launching off the roof of the vehicle. Pieces of a house flying by, and Sean needs to maintain his composure, which he does well, to keep us safe as we're navigating these storms. But our interest in launching rockets into tornadoes and also measuring data inside tornadoes goes back to our observing of suction vortices inside tornadoes. Even the smallest tornadoes, when they interact with the friction of the earth, can split into smaller vortices called subvortices. And they are capable of potentially even producing winds that could approach or even exceed the speed of sound. And shown here are some computer simulations from Dr. Fiedler at the University of Oklahoma. He's simulated the vortex breakdown process. Basically, the balance of a tornado is a very delicate one, and any change in surface roughness or the surrounding environment can throw the tornado out of balance, and it'll undergo vortex breakdown. It can split into these miniature subvortices, and there's many different complicated vortex dynamics that can happen. You can get vortex breakdown bubbles. You get this big bubble burst with a jet-like vortex right below it, a descending bubble as the tornado is losing its force balance above the ground. That descends, hits the ground, spreads out, and can be the entire tornado. But our interest in the 3D structure of a tornado and those subvortices near the ground and its relationship with the mesocyclone above is what led us to develop the method of launching rockets into tornadoes. And we've done everything from ground-based probes to balloons to throwing rocks into tornadoes. And we realized that because of the sheath of sinking air that encapsulates a tornado and leads to the occlusion process, that we really needed the propulsion that a rocket provides so that the rocket can penetrate the sheath of sinking air, or the occlusion process that is especially prominent just above the ground. And then the parachute will pop. And the technology that Mark designs is miniaturized. It's very lightweight, capable of being transported inside of a tornado by the wind speed itself in a Lagrangian framework, which is what we're especially interested in, not just the Eulerian framework of a stationary ground-based probe, but one that's actually moving along with the flow. And we realized that if we could measure high-resolution GPS data inside of the tornado when the probe is moving around inside, when it's lightweight, sufficiently lightweight as Mark has designed, then that is basically at least a very close approximation or a lower bound for the wind speeds that are experienced by that probe. Here's another example of a multiple vortex tornado on May 17, 2013 in Northwest Texas. Sean was driving the Dominator 3 on this day as well, and the roar that tornado emitted when it underwent vortex breakdown and turned into that jet-like vortex just below this section. This is a vortex breakdown bubble as the tornado is starting to weaken. It'll give the subvortex a helical configuration inside. Then you have this jet-like vortex below the vortex breakdown bubble. But it's getting up close to tornadoes like this, whether in Dominators or in beater vehicles over the years, that we started to observe these complex dynamics and also starting to learn the storm structure of the parent supercell, the mesocyclone above, the shape of the supercell, the size of it. And we just noticed that there are a lot of differences in scale and structure from the tornado, from the subvortex all the way up to the mesocyclone. And these are some of the vehicles that we used over the years to chase tornadoes. A 1985 Plymouth Reliant is on the upper left. That was my first storm chasing vehicle up there. Then we had the Chevy Lumina that was held together by duct tape, had a couple of driving lights that were mounted on the front end. And then we built the Dominators. Dominator 1 and 2 are on the bottom on either side. The Dominator 3 is in the middle. And the instruments that are on the roof of the Dominators, that's the whole reason that we built those, so that we can measure data inside tornadoes or close to tornadoes that other people are unable to safely collect. This is my current vehicle, the Dominator 4, which is really on its last legs. I'm going to be putting a flex tape logo on the hood here pretty soon. But I think this year is probably going to be the last year for the Dominator 4. I've got a lot of belts that are slipping in there. The transmission's about to drop out. The sunroof has been blown out as well, but I usually go through about 3 to 4 windshields a year with this vehicle. But now with all the belts starting to slip, once it starts to rain, the vehicle loses its ability to accelerate. So I've got a Tornado behind me moving at 60 miles an hour. Car is going at 40, the belt's squeaking, slipping, not accelerating. And that is definitely a pretty intense situation, even in the Dominator 4. But then suddenly the belt will gain traction, and then I rocket east out ahead of the Tornado. But that's what happened on December 10 and 11, 2021. Here are the Dominators. This is the Dominator 1, and this is actually the first vehicle that I ever purchased from a bank that, you have to get a loan and go through that process with the vehicle. This one was expensive, so I had to go through the loan process, and I instantly turned it into Dominator 1. Didn't tell the bank, didn't tell the insurance company, and made payments for many years down the line, and finally eventually made the last payment without getting in trouble for turning it into the Dominator 1. But that's when we measured the strongest wind speed at ground level, 138.8 mile per hour wind inside of that Tornado. There's the peak wind gust, and these data points here are at a rate of 5 times a second, so 5 hertz. The blue line there is wind speed, the red is wind direction. And I always tell people, when you have a direct intercept from a surface wind perspective, when your wind speed max coincides with a very sharp wind direction shift. When that happens, it's a direct intercept. If there's a little bit of an offset of that wind max with the sharp wind direction shift, then you know that you're probably in the outer circulation, which is, for the most part, what we specialized in. But we were trying to launch probes into tornadoes back then as well, but they just wouldn't work. We were working with a big technology firm, a big engineering company that designed things for defense contracting, and but they couldn't get it done. A probe that would actually work and stream data live. Every probe that we launched into the Tornado would get carried away, and we'd never find it again. And it felt like we were throwing rocks into tornadoes for a long time. And then we met Mark up in Canada, and Mark, as a solo person with his own bare hands, is able to make technology that works. It's miniaturized, records data at unprecedented resolutions, and is able to get a sensor in there that works. I always tell people your science mission is only as good as the sensors that you're launching into the Tornado, and that's why Mark is such an important part of this project, and he's going to be describing the sensors that he built over, what was it, Mark, like a 2-week period, I think, that, or maybe a 1 to 2 month lead time he had, and built those to begin with. And then we launched it into the Tornado on May 28, 2019. Curtis was going around to junkyards trying to find parts and components that he could piece together into a rocket launcher on the roof with pan and tilt capability. He found motors, all different types of parts that he was able to piece together to build the components to launch the rockets. And then you've got the Iceman, Sean, who's able to drive the Dominator 3 unflappable through all conditions and not get that vehicle stuck. You have to do like a 10-point turn every time you drive the Dominator 3. So sometimes he'll shut down roads and everything if Sean was not such an effective driver of the Dominator 3. And here's the Dominator 2 about to intercept the Bowdle, South Dakota Tornado right there. And you can see that corner flow. You have inflow coming in, usually from 2 different sides of the tornado. That's your surface inflow. Then it hits your corner flow and then rockets in a straight up direction. And our goal with the rocket is to get the sensor inside the tornado. The tornado is surrounded by a sheath of sinking air, descending air. Just by definition, a tornado has to be occluded by that sinking air. And we realized through trial and error and using various delivery mechanisms to send sensors into tornadoes that we need the propulsion that the model rocket provides. And that's that rocket launcher that you see on the roof. And now I'm going to hand this over to Curtis, who is going to describe what it's like maintaining the Dominator 3. He's the lead mechanic of Dominator 3, and also the whole process that he went through to design the rocket launcher on the roof with pan and tilt capability.
Thanks, Reed. Okay. As far as Dominator 3 goes, I mean, it's a constant work. We're always maintaining it, keeping it up. A lot of wear parts on it, a lot of movable parts on it, and it goes through basically hell and back. So it takes a lot of maintenance to keep it going, and we stay on top of everything that it needs. So we've done a lot of upgrades since I came on board with Sean. With the doors and with the secondary safety windows and a lot of the wiring and the air drop down suspension and stuff like that. So that's an ongoing thing. It's ready to go. It's sitting in the shop right now. So as soon as we can get south again, we'll it's raring to go. So we did a few upgrades on it just before we got shut down with COVID, but it's definitely ready. The rocket itself, the design part, I think I did over the one winter. Looking at some of Reed's old videos where the rockets would take off when they tried them in the past, and they always seem to want to turn back and come right back at you. So, we have to try and overcome that. They were using rather large rockets as far as length and size goes. These rockets are not very tall. They're about 18 inches. I don't have exactly what it is, but they're rather small rockets. So it was kind of, just a matter of looking at it and going, trying to figure out the meaning to the end, what we want it to do. And the biggest part with small rockets like this is they want to turn into the wind every time. So it's very hard to aim them and get them to go where you want them to go if there's any wind out there at all. So I think I spent about 6 months on a rocket simulator at home, building them and firing them on the rocket simulators, trying to get them to go where in the direction we want them to go, despite whatever wind might be out there. And just playing with the center of gravity, the center of power, keeping those two within one caliber or less than one caliber, about 1/2 of a caliber of the width of the rocket tube. And with working with Mark and the weight of the sensor inside and how we load that rocket, little bit of everything. The biggest problem with the rocket was it didn't ever have enough power to do what we wanted. So we ended up using 2 engines in the rocket instead of the normal one. And we used ammonium perchlorate motors, basically solid rocket fuel, same as what the space shuttle would use. And it produces a tremendous amount of force. And it, every confidence was there that it would work. And the first time we got to fire them, it actually worked. So I'm very confident in the rocket design we have. We have a whole wall of them ready to go south. There's lots of them built, and we're just looking forward to getting back on it.
Kind of a funny story that involves Curtis is when we were about to launch, just 2 days prior to LINWOOD, Kansas, Curtis accidentally shut the very heavy door of the Dominator 3 on his ankle and broke his ankle. So he had to fly him back to Saskatchewan to get that fixed. And then the day after that was the LINWOOD, Kansas tornado. So I had never launched before, and Curtis had to show the whole process. And I had to connect the igniters up to the rocket with the LINWOOD tornado just off to the west, the inflow at my back. And you could hear the roar of the tornado. And it's a miracle that I didn't botch something up with that, because I usually find a way to do that, but somehow I put the igniters on in the right spot, hit the button, and bam, it took off, which was kind of lucky that I think that it was all connected and everything. And 5 seconds felt like 30 seconds too, so time was certainly slowed down. But usually Curtis is the rocket man. So he's the one that will launch the rocket. He pops out the hatch. We have a hatch on the roof of the Dominator. And really quickly, I want to show you the video of our launch, and it'll show Mark in action. He had a receiver that he built that is in a Tupperware enclosure. He was holding out the window with the live data streaming down as we launched into the LINWOOD tornado. And then Mark will describe the sensors that he built, all the technology side of things, and then we'll also share the data that we collected inside of this tornado. We did finish the publication. It's a little bit long at 37 pages, as I mentioned. We're in the process of consolidating that. It might take me about 5 years I see Mark laughing down there, but we are going to get that paper out the door very soon. And now I'm going to show you this video of the LINWOOD launch. I'm sure. There it is. Hopefully this works. Can you guys see it? Thumbs up.
Yep.
We need subtitles for this read.
So there you can see the tornado off to the southwest, trying to get the igniters that were set up perfectly. The key to launching the rocket into the tornado is to aim it at the inflow notch. So this particular supercell was HP, or a high precipitation storm, had a very elongated RFD that actually included a weaker tornado that produced earlier that we were able to drive through in the Dominator 3. It almost got enveloped within the large RFD. And as we turned off to the north, we could see the large RFD gust front, and then it curled right into the inflow notch, where the forward flank gust front and the inflow notch and the RFD gust front that's bulging out meet up. That's where the tornado is. That's where we want to launch. See storm chasers getting out of there. No countdown. We didn't have time for a countdown. And we knew right away that it went inside of the tornado. We knew there was a tornado in there. And then the tornado crossed just to our south, power flashes, and we knew that the rocket simply had to be inside of there. You could see the rocket go right toward the inflow notch of the tornado, deployed only about 400 or 500 feet just above the ground. And then the parachute popped, even lower than that. And the parachute popped, rode the northerly inflow into the tornado, and then did 2 revolutions around the tornado before rocketing up. And listen to Mark. How to do a Ric Flair. Jeez. So there's the receiver. Once we're done. You can see the Tupperware receiver. There's debris flying through the air. So you can hear Mark reading off that data as it was lifting up through the tornado. And eventually he ended up losing signal, and we thought maybe that we lost the rocket forever. But Mark built the sensors so that they will live stream the data back to the ground level at a rate of 1 time a second. But if we can recover the actual sensor, then we can get the 10 hertz data, high resolution data, and the data of the whole entire flight. So we really needed to find and recover that sensor. And we put a post up on social media just showing the yellow nose cone there. And in about 15 minutes, we had a response that someone found the probe in the front lawn of a church in Leavenworth, Kansas, over 30 miles away, 30.2 miles away from our launch point, just to the south of Lawrence. And this was a pretty complicated setup meteorologically. There were 2 different target areas, one near the Triple Point in north central Kansas. That one ended up producing a tornado near Waldo. And then further east, there was an outflow boundary that was in place across northeastern Kansas. And that actually had stronger low-level wind shear, well in excess of 200 0 to 1 kilometer shear. Overall, it was a positively tilted trough. So it's one of those where it is a little bit difficult to pick your target area. We thought it was more likely a chance of tornadoes near the triple point in north central Kansas, but we felt that the threat of a strong, violent tornado, which is the ones that we were trying to find, would be closer to the outflow boundary near the eastern Kansas and the northwestern Missouri area. The low-level jet axis was pushed a little bit to the east of the triple point. So we knew, even though that the storm mode would be more of an HP, high precipitation supercell mode further east, when you're doing science and launching a rocket into a supercell, it doesn't matter if it's an HP or an LP or a classic. Of course, it does matter. That's very relevant information, but we want that strong to violent long track tornado to launch the probe into. And as I mentioned, the key is to launch the probe into the inflow notch of the tornado. You have your bulging RFD off to the south, and this was a large RFD that even had a little embedded tornado inside of that large RFD there. You can see it's an HP storm or high precipitation. Here's your forward flank gust front, the converging gust fronts there. That is the inflow notch where we are targeting to launch the rocket inside. And it actually worked. And there you can see the folks that found the rocket that we met up with, Jeremy and Matt, down in Leavenworth, and it fell right in the church parking lot. He was actually mowing the grass of the church out there. And now I'm going to hand it over to Mark, and he's going to describe his journey of the probes. And then I'm going to hand it over to Sean to talk about what it's like driving the Dominator 3. And that includes intercepting the Coleridge, Nebraska tornado in 2014. I know that driving can be difficult because I can be a little bit loud in the vehicle, doing Ric Flair noises, just blood-curdling screams, but Sean is able to maintain his focus and get the Dominator inside of the tornado. And now Mark is going to describe the technology. Here's one of his beautiful miniaturized sensors that we were able to launch into the tornado just a couple years ago.
Okay. Thanks, Reed. So I was speaking to Sean about another project, and Reed contacted me with the idea of launching sensors into tornadoes, and Project SkyFall was born. So I had a list of requirements. We needed real-time tracking and data, needed to be small and lightweight, indestructible. We had to assume that we weren't going to get the device back at all, so we needed real-time data to make sure we actually got the data. The other thing as well, I had to use virtually no power, and it also had to transmit a long way, and it had to be cheap because obviously we're destroying these things, right? And also failure is not an option. We only really get one shot at it, right? And also you got 2 months to get it done in because we want to deploy in May and it was March. So the first thing we needed was a decent GPS. So I'm just going to put this on. Oh, can you hear that?
We can see it, but can't hear anything.
So did you guys hear that okay? Did you hear that?
I hear you. Not
Or did you hear the sound from the...
No, we can't hear the video.
No. Okay, all right, doesn't matter. So first thing we need was GPS. So we had the sensor position at all times, as it was obviously going Lagrangian. So just there, I was milling a circuit board to do some basic testing. I had to do that because we wanted to make sure we're getting adequate performance from the GPS. This is the first open air test of the GPS. Just check it was working. Next stage, I put a big antenna on top of the house. The neighbors kind of think I'm a little unique. So the next stage was to see how far we could actually receive the data. So with some plastic tubing and duct tape, I mounted the sensor clear of the building. And at this stage, I was hoping for a reception distance of about 5 miles. But we actually got 15 miles on it over ground. And that was through urban terrain with a short piece of wire for the antenna. So at that point, I knew it was going to work. So with initial testing complete, now was the time to work on the electrical design. So 10 days later, this was completed. The sensor samples at 10 times a second, with GPS sampled at 5 times a second. 5 days later, I received back the first batch of blackboards. And you can see there I've got a quarter just for size reference, and you can see the little lithium cell that we powered off down there. Very lightweight, comes in at about 18 grams in total. And then I had to build it, but unfortunately it was a little bit too small for me to build by hand. It would have taken quite a long time to build them all. So what I used was a pick and place machine that I designed to place the parts. And basically it works on strips of parts, which you can see down, the little white strips of tape. And then there's a stencil, which is like a stainless steel. I've got one here handy. No, I haven't got one here, but there's a stencil, which is a piece of stainless steel with holes in, which you kind of smush solder paste through, which is like a solder that's made up of little spheres, very tiny little spheres. Then you put that on the circuit board, then you place the components on top. And this picks up the parts by vacuum and it moves the camera. So you see, it's just placed a pass, it's getting the next pass. So now it's changing the nozzle so it can pick up a different size part. It's picking up a smaller part, so it's going for a smaller nozzle. So then it uses the camera to find the part. And it actually uses vision, AI vision recognition to detect the part. Then it puts it to an upward facing camera to check the orientation on the nozzle. And then it puts it down on the board. And it just keeps repeating that. And this was the first batch of 12 sensors completed. So the boards are now built, but it's a blank canvas, so we need some software written. So this is first light when it was flashing an LED. So generally doing these projects, first thing you want to do, check the hardware works, and first thing you do is flash an LED. It's kind of a rite of passage. So this was on the 23rd of March, so been about a couple of weeks so far. So currently SkyFall allows up to 9 sensors in the air simultaneously with the capability to expand to hundreds. So here I'm just testing reception of multiple sensors at once on the oscilloscope. So we use actually something called time division multiplexing to make sure that basically so each sensor has a slot of time that it transmits in. And they're actually bidirectional. So we get data, the gateway, which is on Dominator 3, transmits and receives, and it transmits a pulse up as a sync pulse. And then the sensors will figure out when that sync pulse is and then decide at which slot it should transmit in. Now it's designed so if it loses transmission, it will go for about 10-15 minutes before they become out of sync. But by then it will generally receive another sync pulse from the station. So SkyFall contains something called an IMU, an internal management unit, which gives us the real-time position of the sensor and the forces being applied to it. So it's got a magnetometer, a accelerometer, and a gyro in it. And this is the first time I was actually testing it. So you can see it follows my movement as I move it around. And these are the, I'm switching back to me here. These are the sensors, just there. And get an idea of the size. These guys are pretty small. So next thing we need to do is simulate the launch environment. So Curtis told me the rockets have been designed. So I went out and bought a rocket and basically built that so I could test it. And so we had essentially the same sensors. So this is May the 15th by this time. By the time all the hardware and software was built. Reed was bugging me to get down there, but wasn't quite ready yet. We wanted to make sure it worked when I got down there. So this is May 15th, ready to test. So I put the call out on Twitter, and a friend of mine called Arthur Byzowski had a farm which we could test at. So we got a permit for the local fire department because we can't launch fireworks here. We've got the sensors for rocket sensing, for rocket testing. So that's the first test. And I didn't have the same engines that Curtis was talking about, the aluminum perchlorate ones. So it wasn't entirely successful in the landing of the tree. It was the only tree that was on the farm, but he managed to find it. And but yeah, the next stage was flew out to Oklahoma on the 18th and met up with Reed, Sean, and Curtis. Here's Reed practicing launch procedure outside one of the hotels. We're pretty lucky no one called Homeland Security on that one. So yeah, so after 10 days, so we were 10 days trying to find a tornado we could put it in. We found 12 tornadoes, trying to find that perfect launch. And the late afternoon of the last day, we found a target in Lawrence LINWOOD on May 28th. And here's the GPS data we collected from the sensor. The blue line is Dominator 3 approaching the site after the rocket is switched on. And the solid red line is track of the tornado. So the original, we got on here EF3, but it was subsequently upgraded to EF4. So it shows it going up. And the green section is when it was under free flight. So the red section is the rocket launch. And you can see it did a loop around the tornado. And then straight up the mesovortex. And you can see the track, the NWS track underneath, and the strength of the tornado as it went along. And that's where it landed. This is example of the real-time data we get back from the sensors. So it's available on a web browser, and typically I use an iPad to visualize the data in real time. So this is the priming scheme we use for keeping up with the sensor. And this actually has tracking information too, so we know how far away it is from us, what direction it is, and we know what speed it's traveling at as well. So this gives you an idea. This one was a test I was running. It was at 49,000 feet, this sensor. And this is more graphical one. I don't tend to use this typically when I'm chasing, but it's useful for the prettiness factor, I suppose. And it gives you the real-time position down below. And yeah, this is the rocket pod we got back. So this is the one that went through the tornado. So one of the concerns we had was, we're putting a paper plastic rocket up there. Is it going to get destroyed by the tornado? But it doesn't, because it flies with the wind, right? So you can see there's virtually no impacts to it at all. And although it was whipping around a EF4, there's virtually no damage at all to it, right? And so this is some audio from within. Oh, you won't be able to hear this, so no point in that one. We actually did some audio from inside the tornado, but you're not going to be able to hear that one, unfortunately. So this is when we recovered the tornado, when we went to celebrate afterwards. Now this is the sounding we took from there. So sorry, this is the Topeka sounding. So this is from close to the time we launched the tornado. And this is the sounding we got from our sensor data. So obviously they're not going to look the same because, the Topeka sounding shows the potential. And when you're in the tornado, things are equalizing. So they're kind of wacky skew-tees, but they're still interesting, right? So particularly the wind, the forces, if you see the rotation near the bottom, you can see as it whipped around the tornado and then as it went up through the updraft. So it got some pretty substantial speeds. And then since then, been doing various other testing. This is let's see if we got SkyFall launch. So this is us all meeting up together at Curtis's place doing some testing. This was some testing we did in Saskatchewan. It was really cold out. I think it was about -20 that day. It shows the launch. Yeah.
You going back to me, Mark? Mark? Hello?
Hello?
Oh, there you are. Sorry, I lost you guys for a second.
Okay. So, so that was a little experiment we did with putting a video camera inside the rocket. We still haven't decided whether it's worth it to do that in a tornado yet, because it's just going to be very similar, lots of going around in circles and grey. But yeah, so what have we been doing since then? So we've obviously got the sensors, and I've been doing a lot of stuff with that. So since that deployment, we've got everything honed down really well now. So I think the maximum I got up to about 56,000 feet, doing tests, SQT tests and things. So let me just put this on here. Let me switch back to me. There you go. So this is what we deploy with now. So it's a little portable battery pack. It's got the receiver in. It's got antenna as well, just a magnetic antenna that sits on the roof. The deployment pack for the balloons themselves. Use this. So these are actually pilot balloons. So they're really lightweight and they're red. And then we put the sensor inside this little pack here, so it's insulated, so we can get it to altitude. And yeah, and then I've got the helium filler there. Those are the things I need, like tape and stuff like that. So basically just these two packs, and we can launch with the sensors. And yeah, and we're kind of diversified a bit now. So now we're doing subsonic. So this guy's for hurricanes and tornadoes. So there's some papers that came out that they had some infrasound detectors where hang on, just switch back. So yeah, so we had some infrasound detectors. They had some infrasound detectors which a tornado went past, and they figured out they can actually monitor, receive infrasound from up to about 1,000 kilometers away and detect when about half an hour beforehand when a storm's rotating and is likely to produce a tornado. So so we came up with this. The only trouble is, since those devices normally cost about $50,000, and if we're going to shove them in a tornado, we don't want to put that kind of money in a tornado. So so we came up with this, which is basically a bunch of piezo discs. It's a phase sensitive infrasound detector, and it uses, let's see what the boards here. Here's some of the boards I've designed. So put it on. There we go. Here's some of the boards. So that's the piezo disc on the bottom. The PCBs that we use in there. We've also got Surgeonator, which we use for hurricanes. It's this guy here. So this goes in. This section goes in the water. This is the station that goes on top. And then we also have Surgeonator, which is a microbarometer. So the thing with these is we're using a microbarometer in all of them. Subsonic has an infrasound sensor as well. And Surgeonator has the depth sensor, and that's basically the tech we have at the moment. The infrasound, so with that we can measure infrasound and gravity waves, and there you can see the frequencies of the gravity waves and the infrasound, because tornadoes give off both gravity waves and infrasound. Reed and other people who've been in tornado have noticed that you get some pretty severe ear popping inside, and often people will hear things inside there as well. It tends to be the infrasound component. It's more of an impulse to the body. You don't actually technically hear it, but you kind of perceive it as sound sometimes. What else have we got? So the subsonic, so it records 0.5 to 10 hertz, and so at about 1,000 kilometers range, and yeah, we got them down to about $400 per unit. And in the future, we're going to be doing tornadoes, more launchers, multiple sensors, and collecting more data. And I'll hand you back to Reed.
Thank you, Mark. So this schematic earlier on, Mark has kind of been making this a reality. The balloon launches, he's already getting soundings. And I can't emphasize enough the importance of having a base state sounding. Thankfully, we had that Topeka sounding that was roughly the same time on the right side of the outflow boundary. Definitely sampled the ambient environment well so that we could derive a pressure perturbation inside of the tornado. But for future launches, we're definitely going to get these balloon launches into the ambient environment to get that very important base state. The ground-based stake probes are basically the gravity wave sensors that Mark just showed you. We're already starting to deploy those inside of tornadoes. And then we're hoping to get Dominator 3 back into the field, launching rockets into the tornadoes, ground-based probes as well. So we're definitely making all of this a reality. And now I wanted to take it over to Sean a little bit to kind of discuss what it's like driving the Dominator, what he has to do, deploying the hydraulics, and just all the different tornadoes that you've been inside, what Coleridge intercept was like. That was certainly a pretty insane intercept over the years. And then I'm going to go back in and then show you a summary of the data collected from the LINWOOD, Kansas tornado. I'm going to show you the pressure perturbation inside of that tornado, the GPS speed, the maximum speeds that we measured, the vertical winds as well. We actually measured updrafts right in the center of the tornado that coincided with the strongest negative pressure perturbation that we sampled with that sensor. So take it away, Sean.
Thanks, Reed. So Dominator 3, it's built on a F350 Ford chassis. And the whole vehicle, we designed it, we built 16 gauge steel around it for the armor. And on top of the steel, it's all coated LINWOOD protective coating just for some extra protection. And all the doors, I have 10 layers of Kevlar just for extra protection for flying debris if we get something that would actually pierce us. And then all the glass was taken out of the windows and we put polycarbonate windows in. So they're basically bulletproof. And it's on an airbag suspension, so that actually when we're inside a tornado, we can actually drop to the ground in like a quarter of a second. Then it's got 2 spikes that actually shoot into the ground about 6 or 9 inches, kind of anchor us in. So when I'm driving Dominator 3, I don't even realize that what I'm in. Like it feels like you're driving in a Cadillac just because of the airbag suspension. Just as comfortable. You just get a little reminder once in a while that people pull up beside you and they're taking pictures as you're driving. But when you're going in for an intercept for a tornado, it gets pretty intense in there. There's a lot of a lot of screaming, a lot of excitement going on. You just got to shut that out and do your job, because at the end of the day, we all want to go home alive. So, but when we're going into a tornado, we drive in, we line ourselves up for it. We get in front of it and we drop to the ground, shoot the spikes into the ground, anchor ourselves in. And then we have a second layer of polycarbonate windows that go up. We deploy that up and then basically hang on. It's pretty intense inside there. Feels like a freight train is driving beside you, debris flying around, you're getting nailed by debris. And it's pretty hectic. You don't see a whole lot in there, but it's pretty intense. We've had a few close calls, but we're still here today, so.
Yeah, you had a close call with that tornado behind your head too, didn't you? That was the Scarth, Manitoba tornado. Yeah, pretty close.
Oh yeah, that was 2 years ago, yeah. Then about 2 years ago, we got caught outside of that tornado. It just formed right above us, and we were actually outside the Dominator, and when it started forming, all of a sudden the dust was flying in there. I jumped in, Curtis jumped in the other side, and all of a sudden we couldn't see anything. We rode it out. It was just dirt flying through. We tried to close the windows, or sorry, the doors, but because the wind going through, we couldn't close them, and we just kind of rode it out, and it was pretty intense. By the end of it, when it passed, there was somebody jumped on my lap, and I couldn't even see. It was just black. It turned out to be one of our shooters for cameramen. But luckily, it was just as the tornado was forming. So I think Reed actually was outside, but he rode it out on foot. But that was another close call, and Giz. But yeah.
Yeah, we also got a lot of cow manure and fertilizer that was lifted off the field by the tornado and then thrown into our face. So I think we had some serious cases of pink eye that we were navigating when Mark came down. And it was actually May 17, 2019. So that was 2 days after Mark's first rocket test up there in the farm. And then he came down just a couple days after that, May 17, 2019, the McCook tornado. And Gizmo was inside that as well. But you never want to be trapped outside of the Dominator when you intercept a tornado. I think that happened about 6 years prior to that during the Bennington, Kansas tornado, when Sean and I had to run barefoot through about 90 to 120 mile an hour winds to get back to Dominator 3 when the Bennington, Kansas tornado was approaching us.
Yeah, Dominator 3, it's still full of corn husks in there. It's been cleaned out many times. I think, Curtis, didn't you wake up the next morning and even, didn't you cough up a piece of a corn husk from riding it out?
Yeah, I had a scratchy throat all that day. I didn't know what was the matter. I went to supper, had a few wobblies, and next morning I got up to brush my teeth and coughed up about an inch-long chunk of corn stalk that was caught in my throat. Yeah, that was quite the ride that day.
Extreme science isn't always glamorous, especially when you're out there in the field getting hit by a tornado and cow manure is getting lofted off of the field. But there's definitely a lot of bad things in those fields, that lofted dust and everything intercepting a tornado. But it is definitely best to be in the Dominator 3 in a tornado, pointed into the wind. You want to try to have the wind going down the main axis of the vehicle. During that tornado in 2009, the person operating the radar named Mick Wimbrow, who was in the back seat, we were in the middle of the tornado and our camera operator looked at him and said, "Mick, your ear's bleeding." And he saw a little stream of blood that was coming out of his ear. And that was actually from the dramatic pressure fall inside of the tornado, such a rapid shift in pressure. And his sinuses were clogged from bad allergies. And it actually ended up blowing out his eardrum, something similar to what a pilot would experience if they were changing altitude very rapidly. So now I want to just summarize the data that we collected inside of the tornado. Mark showed you the GPS position that showed the 2 revolutions around the tornado. Some of the max wind velocities that we measured were right coincident with the EF3 damage. This is Lawrence, just off to the north. This is Highway 59. Our launch point was just to the north of where that tornado crossed Highway 59 and produced EF3 damage. And the strongest wind velocity we measured was in the east side of that tornado, and that is in the same direction that the tornado is moving. And then the probe was pulled near the center of the tornado, supported by the pressure perturbation data. The strongest pressure perturbation, lower than 100 millibars, even about 113 millibars, and negative pressure perturbation near the center of the tornado, supports that the probe was pulled right into the middle and then experienced that dramatic updraft at 65 meters a second, and you can approximately double that to get the speed in knots. But that was one of the first, or if not the first, vertical wind measurement ever inside of a tornado, and it was above ground in a Lagrangian sense. After the tornado did the 2 revolutions, we believe that it was pulled close to the center of the tornado, and then experienced pure mesocyclonic lift, tilted a large horizontal component to that motion as well, as you'd expect with a 100-knot jet streak in the mid and upper troposphere. And then it reached its peak flight just shy of 12,000 meters above sea level before descending down to the ground to Leavenworth, over 30.2 miles away. This is a GPS data summary that includes the maximum velocities that were experienced. You can see we experienced a max 3D velocity, or measured with the probe, of 84 meters per second. The max vertical velocity of 65 meters per second was when that probe was pulled into the updraft portion of the tornado cyclone. And then interestingly, in the lower and especially the upper mesocyclone, the raw 3D velocities were roughly similar between the rotational flow in the actual tornado cyclone and then that tilted uplift in the mesocyclone. It's a much larger scale than the tornado cyclone, so it doesn't really look like it's rotating very much. It's just an intense tilted vacuum cleaner right above the tornado. And it looks like the tornado cyclone exists up to about 5,000 meters before it just enters pure mesocyclonic flow. So like you see in the movie Twister, with a tornado going all the way up and you see blue sky with lightning all around it, it just is impossible for a tornado to maintain that very complex force balance all the way up through the middle and upper troposphere as you're exponentially decreasing pressure. One thing we noticed that was interesting was when the probe was very high up in the troposphere, because of those lower pressures, the pressure amplitudes, those oscillations up there, gravity waves, were much more easily sampled aloft high up in the troposphere than near ground level. And those were coincident with when the tornado was causing EF4 damage, possibly caused by the tornado interacting with the friction of the earth and gravity waves propagating vertically through the supercell storm. But that was one thing interesting that we noted high up inside of the mesocyclone, is that there were some pressure oscillations that were quite dramatic, that were gravity waves that were more easily sampled high up. So here you can see the GPS total speed, and then we split it up into the individual components in the third plot down, and you can see it was clearly rotational flow. You can see that the heading, the bearing in degrees is varying linearly, continually changing, and that's as the probe is rounding around the tornado, constantly changing direction with the rotational flow as it was doing the 2 revolutions around the tornado. And then it was pulled into the middle of the vortex, supported by the pressure data, and that's when we measured the maximum in the vertical velocities. So when the tornado was rotating, the horizontal components were max, but you can also see there was definitely uplift. There was definitely vertical motion that was at the same time as the rotational flow. But then above that, when it got pulled into the middle of the vortex, the horizontal components decreased dramatically, and then the vertical component rapidly increased to a maximum of 65 meters per second. And we categorized the trajectory of the probe into tornado, cyclone, rotational, and updraft, and mesocyclone, lower mesocyclone, and upper mesocyclone based on different characteristics that were sampled during the flow. The lower mesocyclone is when it was experiencing that dramatic tilted updraft. And then in the upper mesocyclone, you started to maximize the overall 3D velocity in a Lagrangian sense of 83 meters per second, but it was largely a horizontal component in the upper mesocyclone. And that's not surprising because there is a 100-knot jet streak aloft. And using the Topeka sounding as a base state, we're able to derive the pressure perturbations inside of the tornado, and they maxed out at about a negative 112.5 millibars right as the probe was pulled into the middle of the vortex, and also just prior to the maximum vertical velocities measured of 65 meters per second. And then aloft, you could certainly see those pressure oscillations, especially in the pressure-based vertical velocities. Notice how these amplitudes are much higher when you get into the mid and upper troposphere. That's because it's lower pressure and you're able to see those gravity waves much more clearly. Gentle oscillations in the GPS vertical velocity are also evident with those gravity waves high up into the upper mesocyclone. And then we began the downdraft as it descended down. We're lucky that the probe didn't become a hailstone that high up in the mesocyclone, but it was able to drop gently and safely down to the front yard of a church in Leavenworth, Kansas, where we were able to recover it. Here's some of the infrasound data that Mark was talking about with the subsonic sensor. I was able to get that relatively close to a couple of tornadoes, especially the Benjamin, Texas tornado. So I put this presentation together just before that, but we actually got it almost inside of an EF3 tornado, and we were able to sample the source of the infrasound. So you could definitely see a strong infrasound signal generated by the vortex itself. And so Mark believes that we use the infrasound sensor to actually measure the source of infrasound for tornadoes. We also use the subsonic sensor to measure the hail roar, which is very audible when you're close to a monster hailstorm that's dropping gorilla hailstones, baseball to softballs. Every single one of those individual impacts accumulates to produce the infrasound signal of a hail roar. And we definitely did notice some saturated infrasound here, at least with the hail roar. Mark is much more effective at describing the infrasound data than I. And to conclude the presentation, this is a photo of an EF5 tornado, Philadelphia, Mississippi. And this tornado was given its rating because it dug a trench through the ground that was 2 feet deep, about 20 yards wide and 200 yards long. So it was actually a strong enough tornado to dig a trench through the clay in Philadelphia, Mississippi. But this was actually from the super outbreak. And you can see how compact that structure is. A smooth transition from the tornado cyclone to the mesocyclone aloft. So if we were to launch a rocket inside this tornado, it likely would do the same trajectory, rotating around the tornado, maybe get pulled into the middle, rocket upward, and then it would begin that tilted descent all the way up to the northeast. I actually include the Dora, New Mexico supercell from Kyle Russell Allen that was taken just to the west of the Texas Panhandle. We include this at the end of the paper to kind of separate the different modes of flow. You can see the tornado cyclone there. Just above it was tornado cyclone updraft. And then you expand, you can see these striations there in the lower mesocyclone that shows you visually the visual representation of those very dramatic vertical winds that happen just above the tornado, where that lowest and strongest negative pressure perturbation is also located. Everything wants to go up, driven by the pressure gradient force, those vertical winds inside of the tornado and the mesocyclone. So thank you, everybody, for having us here at Team Dominator for this presentation, and we would love to take any questions if there are any.